Hi Bobcats! In this video we're going to continue our discussion of Chapter 6 and focus on something known as pressure, temperature, or PT phase diagrams. We'd like to be able to identify the states of matter that are present on each part of a PT phase diagram, and also if we're at a particular temperature and pressure on the phase diagram and we move to a different temperature and pressure, predict what phase transition will occur, if any. This phase diagram is supposed to be a generic diagram showing a generic substance. So let's first take a look at the axes on this diagram. So over here on the vertical axis, we have temperature. Notice they didn't put any specific units or numbers because this is supposed to be a generic diagram. And then on the horizontal axis, we have temperature. So that's where this gets the term PT phase diagram, because it's pressure versus temperature phase diagram. Temperature gets bigger as we go to the right, so that'll be your higher temperature data over there. Notice in this first region, the low temperature region, this region up here, we have solid present, and the little cartoon there is illustrating solid. And then as we move to a higher temperature, so we're transitioning to the right, we end up in the region representing a liquid, and we've got the cartoon for a liquid over there as well. Now, from both the solid and the liquid phases, if we reduce the pressure, so if we move lower on this phase diagram, we end up with the gas phase. So at low pressure, we'll have gases. At higher pressure, we'll have what are called condensed phases, which are a solid or a liquid. There's also another phase mentioned up here, which is called a supercritical fluid. This is a different state of matter that is somewhat like a liquid, somewhat like a gas, and it occurs at temperatures and pressures that are beyond this point here. And notice that this line actually, this line that separates the liquid and the gas actually terminates there at that point, and that point is known as the critical point. Let me go ahead and write that in. That's the critical point. At temperatures and pressures that are above the critical point, so here are the temperatures that are above the critical point, and here are the pressures that are above the critical point. So anywhere in this area that's marked supercritical fluid, that will be the state of matter that exists. Let's see, let's talk about some of these other special points. Down here, we have a point that's known as the triple point. On the next slide, we'll talk about the triple point a little bit more. But the triple point is this really cool temperature and pressure at which the solid, the liquid, and the gas all are stable. Instead of having just one phase stable or maybe two phases stable, all three phases are stable. And then let's see, if we look at this line that goes from the origin up to the triple point, that along that line, we actually have two phases present. We have both a solid and a gas. And so anywhere along that line, we either have sublimation happening or deposition, depending on whether we're going from a solid to a gas or a gas to a solid. If we go from the triple point on up in pressure, that line right there represents melting, because we can have a solid turning into a liquid, or if it goes in the opposite direction, it's a liquid turning into a solid, which means freezing. And then this third point along, or this third line segment along here, I guess it's really more of a curve. Yeah, that's where we have the liquid in equilibrium with a gas. So if we're going from liquid to gas, we call that evaporation or vaporization, boiling. If we go from a gas to a liquid, we call that condensation. Okay, so I think that's it for this diagram. The triple point is something that we're not used to seeing. Normally, we just see one state of matter as the equilibrium state at room temperature and atmospheric pressure. So this demonstration on this YouTube video actually reaches the triple point of carbon dioxide, which is at about 5 atmospheres pressure, and I forget what the temperature is for this one, but it's kind of a neat video to actually see a triple point in action. So I recommend you stop this video and jump over to that one and take a look at that. So I left this clicker question in this presentation to try to illustrate how I can ask questions about a phase diagram. So in class, when I run this clicker question, I ask you to take a look at the arrow and say if we start at the beginning of the arrow and end at the tip of the arrow, so we start here and we end up here, what phase transition takes place? So this is a vocabulary question. We're saying, all right, we're starting in the gas phase and we're ending in the liquid phase. And so for that gas to liquid phase transition, we're going to call that condensation. So that's one way that I ask a phase diagram questions. Another way might be to ask things like, I might give you a phase diagram that has numbers on it for the temperature and the pressure. And I'll say if you start at this temperature and pressure and you end at this new temperature and pressure, what phase transition takes place? I might also ask questions like, which region of this phase diagram illustrates the state of matter in which the particles are close to one another and are in fixed positions? Well, that would be this region up here where we're showing a solid. Or I might ask, which region of this phase diagram contains particles that are separated by the greatest distance? Well, that would be this region where the particles are in the gas state. I might also ask something like, which one of the following regions contain or in which of these following regions are there two states of matter present? And so for two states of matter, it would be any of these lines, this one, or this one. Or I might ask, where are all three states of matter present in equilibrium? That would be here at the triple point. Or might ask, which of the following regions have just one state of matter present, which would be either the solid region, the liquid region, or the gas region. Since PT phase diagrams have such a unique shape, typically on a quiz or a test, I will not fill in where the solid, the liquid, and the gas are located. So that's something that you need to know. I'm going to tell you something that may be a little off color to help you remember this, and I do apologize if I offend anybody along the way. If I do, just fast forward through this. Often this is referred to as a butt cheek diagram, and this linear version that I already drew over here maybe doesn't quite show that. So let me redraw this the way real phase diagrams often are. There's a little bit of curvature into them. So you end up with a diagram that looks something like this. So I hope that helps you see where the term butt cheek diagram comes from. So when we go to assign phases to each of these three regions, think about passing gas. Once you have passed gas, the gas will be available outside of the butt cheeks, and so that is the gas region. Then that leaves us two phases to fill in, a solid phase and a liquid phase. In between those two phases, the solid phase is what you expect at low temperatures and the liquid phase is what you expect at higher temperatures. So that helps us fill in that the solid phase will be over here and the liquid phase will be over here. Just like how we did the heating and cooling curves in a previous video, with heating and cooling curves on a quiz or a test, I usually won't label the phases there either. So you would need to be able to fill in, say for a cooling curve, where is the solid, where is the liquid, and where is the gas. So the low temperature part is the solid, the intermediate temperature region is the liquid, and the high temperature region is the gas. So on this type of diagram, temperature is on the vertical axis. And then here in the middle on these horizontal plateaus, that's where you have the two phase regions present. And so you're seeing the phase transitions on those regions. All right, just wrapping in a little bit of review on this slide. Supercritical fluids are another thing that we don't see commonly, and these form at those really high temperatures and pressures that are beyond the critical point on the PT phase diagram. Supercritical fluids have some real industrial applications as solvents. They're particularly used like for decaffeinating coffee. CO2, supercritical CO2 is used for decaffeinating coffee. One of the cool things about it is that it's infinitely reusable because the caffeine in this will dissolve preferentially into the supercritical CO2, but if you release the pressure and drop the temperature and it goes back to normal gas phase CO2, the caffeine just falls out down to the bottom of your container, and the CO2 is all present there in the gas phase, and so you can just recycle the CO2 and use it again and again. The video linked on this page shows a guy kind of doing this in his garage, generating supercritical CO2. It's kind of interesting, but I do not recommend you do this at home unless you have extreme training in working with high temperatures and high pressures. The pressure is the one that's particularly difficult on this one. All right, let's see if we met our objectives for this video. Wanted you to be able to identify the states of matter present in a PT phase diagram. So see if you can fill in those states of matter and predict what transitions will occur as the pressure and temperature change. So for instance, if you start in this region and you end up over in this region, what sort of phase transition just took place? Right, so to go ahead and answer those, this is a solid, this is a liquid, and this is a gas, and so that phase transition that took place was melting. All right, eat 'em up, cats.